All right, so good afternoon, everyone. Thanks for sticking around past lunch in research day. We have nothing to motivate you anymore. There's no more food. Anyway, so my name is Matt Reuter. I'm here in IACS. I'm also in the Department of Applied Math and Statistics, but don't let that fool you. I'm a physical chemist by training. And so what I'm going to tell you a little bit today are some results ongoing in my research group about reconciling experiment and computation in electron transport studies through molecules. And so we can think about sort of just broadly, since I'm a physical chemist working in an applied math department in a computation institute, what exactly do? I respond to emails, I merge PDF documents, and I invert big matrices. Okay, so basically, research in my group sort of goes in two directions depending on sort of what the starting point was. Where in some cases we use nanoscience in a general sense, so looking at really small things where quantum mechanics becomes really important. And that usually can help motivate us some questions. Maybe they're more chemistry related, maybe they're more physics related. But anyway, what we end up doing is sort of then saying, well, how can we develop some nice models for this type of stuff? And how can we then use these models, whether they're phenomenological, whether they're maybe a little bit more sophisticated, depends on the question we're asking. And how can we dig into now sort of the computational math of what's going on there? Can we find some interesting questions to ask on the mathematical side? Can we find what the physicists might call as an exotic case? Can we find as what the mathematicians would call a pathological case? And somehow relate the two back together. And so sometimes nanoscience makes us look and say, well, what computational math can we use? It turns out there are some really wonderful things in the dusty corners of linear algebra. If you've never heard of anti-eigenvalue analysis or pseudospectra, there's some really cool shit out there, pardon my French. But anyway, sometimes we can use the computational math and come back and find interesting questions to ask in nanoscience. And so the two sort of particular areas that we've been focusing on in recent years, number one, going back to some of my PhD work, is in electron transport. So how do electrons go through some sort of quantum mechanical system? Again, inverting big matrices. Some of the stuff that my two students, Chris and Jonathan, talked about this morning in the lightning talks on nanomaterials sort of start to look at the same thing, and this idea of how do we use modern linear algebra tools to better understand and characterize material properties. And we've been spending a lot of time looking at complex band structure in the last couple of years. At the end of the day, where this all sort of fits together in sort of chemistry, physics, applied math, computational science, is we're trying to develop efficient and accurate algorithms, and in a lot of cases this reaches out to using some very modern linear algebra tools, whether developed for computation, for pure math, or in some cases because of some interesting physical and chemistry questions. Okay? That's sort of the overview of the group. So the title said we're going to sort of compare and try to reconcile experiment and computation. And so when we're thinking about this, the system that we're looking at, we've got some sort of molecule. I apologize, I didn't put a picture on the slide. There's a molecule, there's big electrodes. And we're going to put some sort of bias across and say how much electric current flows through the molecule. I will ruin the punchline for you here and say that experiment and computation do not agree. So most of you, when you're thinking we want to do high-level computation and get accurate results, you're hoping for quantitative accuracy. Maybe you get 2 decimal places right or 3 decimal places right. In the electron transport community, if we could get within 3 orders of magnitude, we'd have a beer and go home and say, that's great. Okay? So there's not a lot of agreement. And there's a whole bunch of reasons in the community that have suggested for why this agreement is so poor. They're all plausible. We don't need to get into them here. The big issue, or two of the big issues that we come is that experiment actually measures one thing, the conductance, the actual property that we're interested in. Computation, in certain limits, can calculate conductance, but in most limits is actually calculating something called the transmission. So basically saying, what's the transmission probability that an electron will tunnel or get from the one electrode through the molecule over to the other electrode? And it turns out those two things, they're not the same thing. There's a reason one is called the conductance and one is called the transmission. Okay? So they can be related through various theories. The simplest one is Landauer-Bodecker theory, where you get the conductance is equal to this constant of proportionality called the quantum of conductance times the transmission evaluated at the Fermi energy. Okay, so they're nice and they're proportional. That's fine and good. Couple issues. So it turns out calculating the transmission is hard. We don't actually know what the Fermi energy is, but we know what the charge of the electron is and we know what Planck's constant is. So hey, we know the constant of proportionality. Go team. Okay, and so in this regard, this sort of complicates doing a comparison because you're sort of comparing, apples and orangutans. All right. So one of the things and advances that we've been doing in recent years is trying to develop new ways, using some of this math and using some of these computational tools, new ways to better compare computation and experiment, recognizing that one calculates transmission, one measures conductance. And so basically the way experiments are done is everything's statistical. We don't need to go into the details of how the experiments are done, but they're extremely uncontrollable. They're irreproducible. This sounds like good science, right? Okay, so the way they get around this is they start doing the experiment, I don't know, 1,000, 10,000 times, and they basically compile just a whole bunch of statistics. It turns out the statistics are reproducible. And so what ends up happening is we get this sort of thing called a conductance histogram. So we've got our conductance that's measured, and essentially how many times we measured it. We get different peaks in it, and we can attribute those peaks to say, well, there's the molecular conductance. Okay, now, a couple things to point out. Full width half mass of this peak is about 3/4 of an order of magnitude. Okay, that's the molecular conductance. Yeah, there's some error bars here. Okay, so the way that these have traditionally been read is you would pick off and say, well, there's the mode of the peak. We won't call it the mode, we'll call it the average. And we'll say that's our single molecule conductance, and just sort of throw out all of this other data. Okay? What we've been doing instead is saying, well, can we somehow use all of these statistics? Number one, can we understand why these peaks have the shapes that they do? The answer is yes. I'll have some references on the last slide. But can we actually use the statistics to actually predict from experiment what that transmission would look like with error bars? And the answer is, again, yes, we can. And so we did a couple of just simple test systems here using simulated data. And actually, now here's a real computation that was done from some of my colleagues at Lawrence Berkeley National Lab and the Molecular Foundry, comparing against experiments done on the same molecule from one of the groups in just down the road at Columbia. And what we're able to find, and so sort of here in the red error bar, this would be the conductance that the computation, or excuse me, that experiment predicted with one standard deviation. And there's the computation that was predicted. This is using the best computational methods that have been developed for doing these types of studies. And when you go and look at their paper that was published, probably about 3 years ago on this, they're very sad that there wasn't, they weren't right on top of each other. But the issue is the computation is within 2 standard deviations of what the experiment would predict. So they're sort of crying and saying, we weren't really on the money. And I'm like, I don't think you can say you weren't on the money. You're within 2 standard deviations. And you're right at 2 standard deviations. But you're right there. But what we've ended up doing is finding better ways to do the comparisons so that we can actually try to put both the conductance and the transmission on equal footing. Okay? So that's sort of one area. Another one that we're doing, sort of coming back towards the computation, is how do we do better computations? It's possible there's something wrong in our computations that might contribute to these 3, 4, 5 order of magnitude difference that we sometimes get between the computation and the experiment. And so it turns out, if you start digging into the literature, there are some well-known numerical artifacts in these transport calculations. They know, for instance, that you typically don't get basis set convergence, so you throw more computational resources at your problem, and it basically turns into a random number generator. Your number doesn't converge, it just sort of keeps flopping around like a fish. That's usually not regarded as a good thing. There's another thing called ghost transmission, a numerical artifact where you basically say, take the molecule out of the system, but just leave like a 3 nanometer gap, and look at this tunneling transmission probability, which Physics 1 student could figure out that the probability of the electron getting through that gap is 0. It's not, well, it's like 10 to the minus 120th, but we can all call that 0. Okay. And so you can then go and actually employ the common state-of-the-art techniques on these systems and actually find that the computation produces a transmission probability of 1 in 10. That's close to a 10 to the minus 120. Right? Okay. So what we've been doing in recent years, and this is very much ongoing work with Panu, who's here in the audience, is trying to develop and implement different solutions for how do we, number one, figure out what are the causes of some of these problems. That's been, well, Robert and I hypothesized on this a couple of years ago. It's been a bit more fun. But working on the implementation now and to demonstrate that not only can we understand where these numerical artifacts are coming from, but that if you'll let me use the verb in a scientifically appropriate context, we can exorcise ghost transmission. Okay. And so what we've plotted here are some preliminary results from a few years ago, where basically in the black line we've got sort of what the traditional codes are saying you would get for the transmission. All of the jumpiness doesn't matter. In the gray line is where we sort of use our fix, and what you sort of see, sorry, other way around, black line's the fix, is that in general, when you put in this fix, things sort of shift down a little bit, and we can start to account for why things are a little bit higher than what they would want, what they necessarily should be. So anyway, I will end there and just put up the slide. Thank Panu for his ongoing work. Stephen Schutte was an absolutely phenomenal undergrad here about 2 or 3 years ago who helped do the conductance histogram work, and my colleagues and collaborators, Torsten from University of Copenhagen and Robert here. So I'd be happy to take maybe one quick question if you have any. Thanks for your attention.
Don't you think that the most important aspect for the differences that you observe between theory and experiment is the detailed knowledge of the attachment of the molecule to the leads.
So that is certainly very much. So the question was, for other people in case you didn't hear it, is the actual geometry of the molecule and the electrons important? Absolutely it is. And so the issue, though, is if that were the only factor, I would argue that half the time experiment would be lower than theory and half the time it would be higher. To me, the fact that computation is always 2, 3, 4, 5, 7, 8 orders of magnitude bigger tells me I think there's something else that's a little bit more systemic and pernicious going on. I mean, I can't discount that factor. It's certainly a plausible explanation, but I don't think it's the only one. All right,
Thank you very much, Matt.